80%, yeah, 80% of the really common compounds are all exceptions that they named before they came up with the rules.
Yeah,
so you have to like memorize an absurd list of compounds that all break the rules.
That sounds like chemistry.
Maybe you don't know.
Regular
I'm real sorry.
Physics department, they're like, we found your photocopy. You left your photocopy on the copier in the lab and everything. Like, because the physics department's so small, like every time there's this stuff, I'm talking about.
Why are you asking about that? Is something wrong with the pen?
No, pen works fine, actually. I'll explain. We're going to be doing something a little different in class. Not today, but on Wednesday. So.
Hey, Brooke, who's missing? Oh, wow.
Wait, what?
That's what I saw.
Where did you get that? I need one. I need 4.
What does it say?
He's like, where did you get it?
Okay, everybody, please turn in your homework for the day. We're going to go over that and pick up the solution, which we'll also go over. Let's do that first. Okay, so this is an example of a problem involving torque. An example of a very simple rigid body, which is simply a mass at the end of a fixed rod. So you're not going to consider in this problem the mass of the rod. So this simple example, all of the mass of the pendulum is concentrated at the end, in this bob at the end here. So we're going to neglect the mass of the rod. We can go back and do this problem again later, putting in the mass of the rod, but the principle, it'll be pretty easy to do that once we establish how to do these kinds of problems. Now this is an example of kind of rotation, the way we're looking at it. It's a kind of rotation, and so we'll measure the swing of the pendulum by the angle from the vertical. And swinging it to the right would be positive angle. Okay, and this pendulum swings in a plane, and so this is called the plane pendulum. Meaning you could have a pendulum which doesn't swing only in a restricted plane, but which could, for example, if you were to hang a mass from a string from the ceiling, you could have it swing like this, right? It could move this way, or some more complicated motion, right? It can do all kinds of things like this. This is swinging in a plane, so the motion is restricted to being in a single plane and not doing something else. And the plane is the plane shared with the rod and the hinge top. So there's only one variable needed to describe where the pendulum is, and that's the angle from the vertical, and that's theta. Okay, now just looking at this then we're going to write Newton's equation, but the analog to Newton's equation for rotational motion. So what is the analog to Newton's equation for rotational motion? Volunteer. Mr. Vestal.
Torque equals dl dt.
Good. So instead of, I'm going to write it dl dt. Yeah, no, that's fine. Like that then, yeah. Net torque equals dl dt, and the three-dimensional version of that would be a vector form. The vector torque is equal to the derivative, the rate of change of the vector angular momentum. Who have I caught? I know who I caught. I don't know.
It's always the same guy.
Yeah, it's always, I know, it's always the same guy. Are we all right? Okay. Turn your music on. Whatever it is you're listening to. Okay, so let's look at the two. So there's two parts that we have to look at here: the angular momentum. You can turn that down, please. The angular momentum and the torque. Okay, so let's first look at the angular momentum in terms of the one variable that we have, which is theta. So if this thing is swinging to the right, that is, if theta is increasing, then the velocity is like this, and the momentum is also that way. And if we calculate, notice that we need to select an origin from which we're going to calculate both the torque and the angular momentum. We need an origin. And all of these problems involving rotation, I must specify the origin. Absolutely necessary, because the angular momentum depends on the choice of origin. Now there's usually, and the torque as well. Now the choice of origin is usually very obvious, but not always obvious. In this case, there's an obvious one, which is the hinge, because the thing is swinging around the hinge, and we're considering rotation around the hinge. That's an obvious, natural choice for the origin. Okay, so I'm going to choose that. If you had chosen a different origin, then the problem becomes more complicated, and you'll see why in a minute. This makes it much easier. For a real good reason. You'll see why in just a minute. Aside from the fact that it's kind of the obvious place where the thing is swinging around. Okay, so having picked that as the origin, let's now look at R. There's the R vector. That's the position vector. And then the momentum vector. Now, given that the momentum is out in that direction, so what is the magnitude and direction of the angular momentum? I'll switch back to black here. What is the magnitude and direction of the angular momentum? So let's do, remember, it's R cross P. So in what direction is the angular momentum?
Perpendicular.
It's perpendicular to the paper, right? It's perpendicular to both R and P. R is down like this. I have a little trouble doing it, but it goes down like this, and then you curl your fingers into the P. R cross P, it's out of the board. And with the velocity in that direction, then the angular momentum is out of the board. If the pendulum is swinging the other way, what is the direction? If it starts to come back down, then the direction of the angular momentum is R cross P into the board. So it's either out or in the board. So and we'll choose this direction, call it Z, so that angular momentum this way is positive, angular momentum that way is negative. Okay, so what's the magnitude of the angular momentum then? If it's R cross P, are P and R perpendicular to each other? Yeah, it is circular motion, isn't it? It's not uniform circular motion, but it is circular motion. The velocity is perpendicular to R for circular motion. So what's the magnitude of R cross P? In general, for a cross product, what's the magnitude of R cross P in terms of R and P? Mr. Disharoon.
MR squared
Yeah, you're anticipating some. I'm just trying to get, before we get to that step, what is the magnitude of R cross P? What's the cross product, the general expression for the cross product in terms of two vectors? RP sine theta, and the direction is the normal formed by 2, right? So the magnitude of R cross P is RP, and what's, okay, different theta here, different angle here. What is this angle that's present in that expression? It's the angle formed by R and P, right? Not theta, not the angle where the pendulum makes with the vertical. The angle that's in the cross product is the angle between R and P, and what's that angle? Right, sine of pi over 2 is 1, so it's just RP. Magnitude is just R times P, and P is mv, so it's just mRV. And what is V in terms of theta dot? R theta dot. Thank you. So this is m r squared theta dot, which is what Mr. Disharoon was trying to tell me, but I didn't want to go quite that fast. Okay, I wanted to slow down and build up to it. mr squared theta dot. Okay, so in terms of the angular momentum, the magnitude is mr squared theta dot, and it's in terms of z hat. This is coming out of the board, so let's write it down in terms of z hat. The vector is mr squared theta dot z hat, where z hat is coming out of the board. Okay, now r squared happens to be L. Okay, I chose to call it L as well, so I could also write it as ml squared. I think that's what I used, ml squared. Okay, r is constant. Doesn't change. It's not a stretchable pendulum rod. If the pendulum rod were a spring instead of a rod, this would make it an interesting problem. The mass is oscillating and swinging at the same time. We could do that problem sometime. Yes, sir. Mr. Vesta, do you have a question?
Okay, the magnitude of the L
Yes, sir.
is, how can it, theta dot is omega, right?
Yes, sir.
And V equals R omega.
Yes, but notice that omega...
Oh, I missed the square. Never mind.
Okay. And notice that omega is not a constant here, right? There is angular acceleration going on and deceleration, depending on where it is. In uniform circular motion, theta dot, which we called omega, was a constant. It just goes around and around and around and around. This pendulum doesn't do that. It swings like this. So theta dot is not a constant. Omega is not a constant. The next derivative of omega is called alpha. The angular acceleration is not a constant. It keeps changing. Okay? So, keep that in mind when you write these things. Yes, ma'am, Ms. Shaven.
Why was the velocity r theta dot again?
Right. So, remember the velocity generally is r omega, where omega is theta dot. So let's, if you want to verify that again, let's go back to the argument of something moving a slight distance. Okay, moving a little distance. So this is delta theta. Swing at just a little distance. What is this distance here? If the radius of the arc is L. What is the arc length? No, L times the angle. L delta theta. So the distance that it moves along the arc is L delta theta. Let's divide by delta t to get the speed. The velocity. So the velocity then is L theta dot, or R, generally speaking. That's an important relationship. The arc length, the length of arc, if I take a radius and draw out an arc of angle theta, the arc length is L times the R is R times theta. Okay? It's a general relationship for a circle. Is that unfamiliar to you? We've been doing it since the beginning of the term, but maybe before this class it was not familiar. Okay.
How come we use omega and theta kind of interchangeably?
No, omega is theta dot.
Right. But
Just like V is x dot. Right?
So we don't use like I don't know, I guess.
So the analogy would be x and theta. V is x dot. Omega is theta dot. Alpha is v dot, which is x double dot. I'm sorry, a is, excuse me, a for acceleration. We use that symbol. And the common notation, I mean, you can invent your own, but the common notation is to call that alpha is omega dot is theta double dot.
Oh, okay, it's just a difference.
So is omega not changing?
Omega is changing in this, yes.
So how do they say like omega is equal to the square root of g over L or something?
Ah, okay. We'll come back to that question. Different omega. It's a different omega. It's something where we're using the same symbol to represent two different things. And there's a confusion waiting in the weeds to get you. Like the snake that my kids found in the laundry room. We haven't had any laundry for days. My wife won't go in there anymore. So I'm starting to reuse clothes.
Oh, instead of doing laundry?
That would be worse than... I should just let the snake do the laundry.
Is the snake still in there?
No.
Okay.
Oh, but the memory lingers.
Memory.
All right. So, there we are. We got the torque and the angular momentum, right? Now, as Mr. Averett points out, we use this symbol omega here as theta dot, but we're going to use it. There's another omega here, which is left over from the simple harmonic oscillator, right? The simple harmonic oscillator, we had the frequency of the oscillatory motion, but there's no angle in the simple harmonic oscillator. It's just the thing moving back and forth. But we use the symbol omega to represent the frequency of oscillation. So there's confusion waiting for you here. We're using this. Possibly, don't do this. Don't make this mistake and use the same symbol in two different places to mean two different things, because you'll get yourself. It's confusion, isn't it? Right? Two different things that are thought to be the same. They're not. So. Wait, you've got to watch out for that. In the chapter on the simple harmonic oscillator, omega meant the frequency of oscillation. And the chapter on rotation, omega means theta dot. Different thing. It's just made for confusion. And it's just very common. And so it's just something you're going to have to kind of work with and recognize, because the notation is very common.
So what does omega mean?
It depends on the circumstance.
So in the pendulum,
So it's not, it's a constant if it's in a circular motion.
Uniform circular motion.
But it's not if it's trying to talk about like the pendulum or something.
In a pendulum, omega is not a constant. Right? Just like the velocity of a body that's accelerating is not a constant. Right?
So what does the square root of g over L over g have to do?
I'll get to there. We'll get there. It's the frequency of motion, frequency of swinging. Hold on. You're introducing something I haven't done yet, right? You're trying to remember something and you're going ahead of me here, so slow down. Okay, and it will all be clear if you'll just be patient. Okay, now the next thing we have to do is calculate the torque. And the torque is R cross F, and so we have to look at the forces. Time to do a force diagram. Let's look at the force diagram for this body hanging from the rod. Here's the mass. Here's what forces are present on the pendulum, on the bob.
What's the tension?
The tension in the rod, you could consider it to be a rope or a rigid rod, but there's tension. Even in the metal rod, there's tension present because. And what else? Gravity. Two forces acting. And I should draw my origin again up here. Here's my origin. And so here's the R vector. Okay, so I have torque due to each force. We're looking at a net torque, and there are two forces, so there's a torque produced by each force. So let's look at the torque due to the tension in the rod and the torque due to gravity. Okay, R cross T and R cross mg, where this g is down. Okay. So g is the down vector. Acceleration due to gravity is that way. Okay, what is R cross T?
Zero.
Why?
Because they're
They're anti-parallel. And here's where you should be able to see. In order to calculate the torque around that hinge, you don't need to know the tension in the rod. And the problem simplifies. If you put the origin anywhere else, or anywhere else, the problem becomes more complicated. If you put it somewhere else, you might have to compute the torque due to the rod, to the tension in the rod. So there's torque present or not, depending on your choice of the coordinate system. Remember, this is torque and angular momentum, and these things are just expressions of forces and momentum in a rotating system. There's no new physics here. It's simply expression of Newton's second law, but in the case of where we have rotation. That's all we're doing. And so having chosen an origin by which we're going to say it's rotating, now that's going to determine what we call torque and what's even zero torque, okay? All right, so the next thing we need is R cross mg, so this is going to be mg, R is L, and now we need the angle between, the sine of the angle between R and G. And what is that angle? Let's extend this out. This is the same angle theta, isn't it? It's the same angle. And direction is, now in this case, which way is the torque acting? Is it out of the board or into the board? Mr. Vestal almost has to come out of his chair to do this. Right? Do it behind your back, might be easier.
So what's going into
It's
what?
into the board. R cross G. Into the board.
Okay.
R cross G. Put your fingers along R and curl them along G. And your thumb will point in the direction of the cross product. So, there's a negative Z hat here. Okay, so now we're ready to go. Let's go back to the equation. We had torque was equal to dl dt, net torque, and where we chose to compute both the angular momentum and the torque, in other words, our origin for this problem, we don't have to know the tension in the rod. How convenient. That makes it much nicer to deal with. So, the torque is then that, and the angular momentum is mL squared theta double dot. Right? If L is mL squared theta dot, then the derivative of angular momentum involves theta double dot. Right? The mass doesn't change, the length of the rod doesn't change. So L dl dt is just mL squared theta double dot C hat. Okay, so looking at it then along the x direction, this is my equation of motion. And you could write theta double dot, you could write alpha for theta double dot. If you want something that looks like F equals ma, instead of a, there's alpha. And mL squared there is the moment of inertia. And the angular acceleration and the torque. So you could write it that way. The torque is I alpha. That's the analog to F equals ma. Torque equals I alpha. I, the moment of inertia of that bob hanging at the end of a rod of length L, is mL squared. Okay, so I could write it in summary form, tau equals I alpha, or in terms of the other parameters that we were given, G and L and theta. Looks like that. Okay, now I'm going to divide by the mass. I'm going to divide by a length, length squared. So what I'm going to get there then is square root of G over L sine theta. I'm sorry, negative G over L sine theta. Theta double dot equals. That's now summarizing my equation of motion, reducing it to its simplest form. Okay, now that looks almost, let's do a dimensional analysis before we check out here at the next step. So what's the dimensionality of the left-hand side? Theta double dot. What's the dimensionality of that? What's that?
Something t, negative 2.
Right, so remember it's the second derivative with respect to time. It's a fraction. Something over time, something over... Yes, right. Angle is dimensionless. Theta dot is inverse time. Dimensionality of theta double dot is t to the minus 2. Every time you take a derivative with respect to something, then you get that something in the denominator. It's a fraction, right? Change in something over change in something. So it's just a fraction. And the angle is dimensionless. Okay, how about the dimensionality of G? Thank you. L over T squared. Dimensionality of the length of the rod? Well, so the dimensionality of the right-hand side is inverse times squared, matches the dimensionality of the left side. That's good. The sine of theta, well, theta is dimensionless, and the sine of an angle is also dimensionless. There's no dimensionality to it, so that's good. Checks out.
How come you use L interchangeably with R?
Because it's fixed length. And I started off writing L, and then I wrote R, right? So you can use either one. R is equal to L. It doesn't change length. I expressed the problem originally in terms of L. I said there's a pendulum of length L, and that's why I keep going back to L.
So it's only for a fixed length, right?
Yeah. So we could invent a problem where the thing doesn't have fixed length. It could be a spring. And this mass is not only swinging, but it's also oscillating on the end of the spring, right? It could get more complicated. That would be a kind of interesting problem to do. Not yet. We'll get there. Maybe we'll get there. Okay, now this is not very easy to solve. This is not one of the ones we have seen. This is a differential equation. It's not one of the ones you have seen yet. And it is why this is not a simple harmonic oscillator, because it doesn't have even the same differential equation. Let's review the differential equations you have seen. X double dot is 0. That corresponds to a mass with no force. Uniform linear translation, right? Newton's second law for that case, no forces. Maybe I should write it the other way around. It's the physical situation that gives rise to, so no force. We can write Newton's equation as x double dot is 0. That's uniform linear translation, right? Constant force. X double dot is a constant. Uniform linear acceleration. Polynomial, quadratic in T. We've done simple harmonic oscillator. Oops, minus omega squared. So the force, Hooke's law, in other words, the force is proportional to the displacement. It's not a constant force, it grows in proportion to the displacement. That leads to simple harmonic motion. Now we have this equation. Doesn't fit any of the previous types of equations. The force changes with angle, but not linearly with angle. If I double the angle, the sine of the doubled angle isn't double, right? So it's not Hooke's law. It's something else. If I plot the force, the torque as a function of angle, the torque will look like this. It actually turns over. The torque as a function of angle actually turns over and becomes positive here. And that's when the pendulum has reached the top and is now past the top, the torque is going to make it keep going around, not make it come back, right? If I pull the pendulum up to here and let go, the torque restores it back to the bottom. If I pull it up here, the pendulum restores it. Gravity keeps pulling it back down until I get it past the top, and then instead of pulling it this way, it now makes it go over the other way. So it's not Hooke's law. It's very strange. It's a different kind of force law. You don't know how to solve this differential equation. I don't imagine anybody in this class knows how to solve this differential equation. It's a tough one to solve. Okay? All right, so now, however, let's make a following approximation, which we know physically, that if this pendulum that I've got hanging from the ceiling, if I just pull it a little bit to the side and let go, it resembles simple harmonic motion. It's very close to it. So if theta is small, always, then I can make an approximation to this where in the equation of motion that I have, I could replace the sine of theta by theta. It's called the small angle approximation. If theta is small enough, then the sine of theta is approximately theta. So this is the small angle approximation. Sine of theta is approximately equal to theta for theta small. The next correction to that is theta cubed over 6, I guess. So it has to be, you can compare the sizes of those terms. Theta cubed over 6 has to be much less than theta to get rid of it. So theta has to be much less than square root of 6 radians, I guess. So if theta is much less than a radian, much less than a radian. Really, it's something like, if it's less than 10 degrees or something, then you can get away with this approximation. Okay, so let's suppose that the motion is always small. And in that case, the equation of motion now, I can replace the sine of theta by theta. And now I have something that should look familiar to you. That should be what? Just a minute. What is that? That's the simple harmonic oscillator. Now, there's in the simple harmonic oscillator, we used the symbol omega to represent the frequency of motion. I can't use omega in this problem because I've already used it to represent the derivative of theta. So the frequency of motion, though, the frequency of swing, is equal to the square root of g over L, just like for the simple harmonic oscillator with square root of k over m. The frequency of the swing and the period of the swing is equal to 2 pi over the frequency, or in other words, 2 pi root L over g is the period of swing. How long it takes for it to swing back and forth. Don't use omega for that symbol, because you've already used omega in this problem for something else. Okay? You're free to use symbols as you like. Just tell me what they are, but be careful. Using two symbols for the same thing might not be disaster, but using one symbol for two different things, you're just waiting for trouble. It's coming. You're about to make a mistake because you're going to switch. So, but it's very common to use omega. In general discussions, omega, you'll see frequently refers to the frequency of an oscillator, or it refers to theta dot. You see it both notations in both cases. You just got to be on your toes.
How come you take the square root?
Because if you remember from the simple harmonic oscillator, x double dot is minus k over mx, and then the frequency of the simple harmonic oscillator, I shouldn't write that. See, there we go. The frequency was root k over m. Just by analogy to the simple harmonic oscillator, frequency of the simple harmonic oscillator was square root of k over m. It's mathematically the same. The second derivative of something is equal to some constant squared, negative some constant squared times that something, right? So we've got x and x double dot before. Now we've got theta and theta double dot, and we just got this constant. Notice that the frequency of the swing doesn't depend on the mass. The mass has dropped out. That's because gravity depends on the mass, and so does the moment of inertia. So it drops out. And notice also that it doesn't depend on the amplitude of the motion. That if I take a small angle pendulum, I pull it out just a little distance from vertical and let go, it's going to swing. And if I take a second pendulum and I pull it out twice as far and let it go, they'll stay in sync for a long time. Not true if I take one that's way up here. Take a little pendulum that's just a little bit out here and take another one that's way up here. They'll get out of sync really fast. And that's because this small angle approximation doesn't work for that case. For the second pendulum where I pull the pendulum way out here, I have to use the original equation involving the sine of theta. And there, the amplitude of motion comes in. And so I don't have the same, it's not a simple harmonic oscillator. Okay. Yes, sir, Mr. Kelly.
Did you use like Taylor series?
Yeah, this is a Taylor series here. For those who are familiar with Taylor series, I wrote down this is the first term of the Taylor series, and then this one is the first two terms of the Taylor series. We haven't covered Taylor series here, but it's a way of approximating functions. And so the first term in the Taylor series, what I want then is theta cubed over 6 to be much, much less than theta, so I can drop it. Theta cubed term. In other words, theta squared has to be much, much less than 6. Theta to be much, much less than square root of 6. Or I was conservative, I said 1 radian. It's much less than 1. So typically 1/100th of a radian or something will be small, very small. And that's, 10 degrees or 5 degrees or something. Okay, so the pendulum, in general, is not a simple harmonic oscillator, even though it's periodic motion. Right? You take a pendulum, put it up here, let go. It's periodic motion. But the difference is that the amplitude, that the frequency of motion, the period of the swing depends on the amplitude of the motion, how big the angle is. Whereas for a simple harmonic oscillator, the amplitude of the motion does not affect the period of the motion. And go back to chapter 6, you'll notice the period of the motion doesn't depend on how big the swing is. If I double the stretch in the spring before I let it go, it's got the same period. If I take two simple harmonic oscillators, one stretched 1 meter and the other one stretched 2 meters, and I let them go at the same time, they'll stay in sync with each other forever, as long as Hooke's law is valid and there's no drag and all that, all of our idealization. They're going to stay in sync. If I do it with a pendulum, though, as long as both angles are small, they'll stay in sync. But if I get one of them big, it'll get out of sync with the other one really fast. The periods of motion aren't the same. Yes, sir, Mr.
Is there
Fisher.
like a certain threshold for what, like that?
Yeah, right about there. Square theta's it's going to be a gradual process, right? So they're going to get out of sync if you wait long enough. They'll get out of sync. It's just how long you have to wait for them to get out of sync gets shorter and shorter. And so it's really a question of how long you're going to wait to see that they're out of sync. It's not a threshold in the sense that it's a sudden thing.
It is too gradually decreasing.
Yeah, it's a gradual process. Okay, so the point of this exercise is two things. One is it's an example of torque and angular momentum, the relationship between torque and angular momentum, and the other is the understanding of this as an example of a simple harmonic oscillator if the angle is small. And so now you need to go back here and examine the torque, right? So this thing is going up, the angular momentum is out of the board, but the torque is into the board. So analogous to force, it's reducing the angular momentum. Analogous to what force reduces momentum, the torque in the opposite direction to angular momentum reduces the angular momentum. So it's analogous to linear motion, where we had a force present. Okay, and so then it drains the angular momentum. All the angular momentum is taken out. It stops, but there's still a torque acting on it into the board, and that torques it, makes it start to swing back. Right at the bottom here, the torque has gone to 0, but it has a maximum amount of angular momentum, and it overshoots, keeps on going. Overshoots, now the angular momentum, the torque is now acting, angular momentum is into the board. When it's swinging this way, the angular momentum is into the board. But the torque is now out of the board. And it's, again, opposing the motion, so it slows down, stops. Now there's torque this way. Torquing it back, starts to go back. Now the torque is decreasing. 0 torque right here at the bottom, but now it's got angular momentum. It's going to keep it going that way. See, it's very analogous to what we were saying before for force and momentum. But it's an analog. It's an analogy, right? And like all analogies, it has its limits. Angular momentum is analogous to momentum, and torque is analogous to force. But you understand that there are limits to the analogy. Okay. Any questions about this? Okay. We're at a bit of a crossroads here. the tests I have to test here, I'm going to hand them out, frankly, lousy. The last two tests have been lousy, and I had kind of an excuse on the last one in the sense that the instructions might have been confusing and created a longer test than you had time for. But even looking at the two scores, the two tests together, there's weakness. There's a lot of weakness. I'm not happy with where the class is right now. I've taught this, this is my fifth or sixth time, something like that. Virtually the same material, same test. It's really not that different. What's different is that y'all are first semester freshmen instead of second semester. Maybe that's part of the explanation. I'm not really sure. Every class is different. I got 15 different people, 16 different people, different personalities. Something's different this time, right? But it's a pretty marked difference here. I'm not happy going forward at this point with the way your understanding is at this point. I think even going ahead, I mean, we're about to do in Chapter 7, we're about to do, the analog to, we've started here, the analog to Newton's equation here. Equation of motion. We're going to be doing that for rotation. Then we're going to do kinetic energy and the work energy theorem for rotational motion. But if you don't understand the work energy theorem for translation, I think the analogy to rotation is going to be not real solid. You're not going to be able to build on your understanding of work energy. So this is what I'm going to do. Here's what we're going to be. I haven't done this before, never done this before, but I've never taught a first semester class before, so this is going to be an opportunity for you to take a pause in the course material, not from working. We're just not going any further ahead in the book. In fact, we're going back a little bit. Okay. I'm not explicitly going back to Chapter 2. There's still weaknesses in dot products and cross products. You've got to get that fixed, right? That's just going to have to be fixed. You've got to do that. You've got to figure it out. People doing dot products when they should be doing cross products, and cross products when they should be doing dot products, or getting them all confused with each other. That's also, I see a lot of that. That's got to end. You've got to figure it out. That was Chapter 2. We're trying to go to Chapter 8. You've got to fix this up. Okay? You're going to be doing these simple vector stuff in spades in the second semester. I mean, we're going to have a whole bunch of that vector stuff coming when we're doing electricity and magnetism. So you've got to get this fixed in your mind. But in particular, what I'm going to do is the following. The assignment sheet for Chapter 7 is null and void. I'm going to redo that. Your assignment for Wednesday is the following. You're retaking the test for Chapter 1 to 4, but it's not, this is not graded, not for grade. You're going to study, you're going to redo, but it's not a redo for grade, right? You're going to look at, review, re-examine, that's not re-examine, the test for Chapters 1 through 4. Okay? Then I want you to do it. And then you've got the solution in your email box. I want you to grade your own test. Bring your graded test to class on Wednesday. Graded test to class. I'm going to use, you're not going to turn it in. This is purely for yourself. And if you put work into it at this point, you'll get a lot out of it. If you slack off and do nothing, you're not going to get any better. All right? And you're going to be left in the dust. So bring your graded test to class. We're going to work on them here in class together. I'm going to assign problems for people to go up to the that's the second question here. We're going to, hold on a second, we'll get to that. Yeah, might as well say it. I'm going to assign, you're going to do number 1, number 2, number 3. So we have two different places we could do that. We could do it here, and I could use the document camera and take somebody's test, Mr. Creer's sheet, put it up here and for everybody to see. Okay? We're putting you on the spot. And then we're going to pick it apart. We're going to comment about it. Now, he's had a chance to compare it to the solution and stuff, right? So it's up to you how much of that you want to do. Do you want to open up the book, figure it out? Do you want to look at the solution and figure it out? Don't bring in a copy of my solution, though. All right? There's no point in doing that. I know how I'm going to grade that, right? There's no point in doing that. So, but I'm leaving this up to you. The quality of this exercise is up to your own judgment here. The best thing for you to do is to try to do it on your own without looking, and then grade it, and then bring that in, right? So I could see that you can see that it wasn't right or something, right? In what way it was wrong or something. And everybody can see it, okay? Now we could do that in one of two places. We could do it here with a document camera, or we could go back to room 223, which was the room we started off in this year, which has 3 blackboards. And I could put 1 person, 2 persons, 3 persons doing it at the same time, writing it up on the blackboard. Which would you rather do? What do you think? Kind of like having 3 blackboards. That's not bad, but we can kind of work in parallel. But if you're just bringing me pages you've already written out, that's pretty quick. What do you think?
Yeah, the blackboard seems more efficient.
I like writing.
You like blackboards? I like blackboards.
Yeah, I like
It seems
whiteboards
like
better.
easier to go
I think that
over
would
it,
work too better.
like on the blackboard versus like you've already written something down and you're going over it and you have to change something you've already
Because
written
I think it makes sense that more sense to go through the process by writing it instead of saying, all right, so here's this line, and then I got
Here's
from
the
that
next
line to
line.
this line by doing this. It makes more sense to just sort of write it out piece by piece.
Okay.
Talking about it.
All right. So we'll do it on the blackboard. That will give you the chance to explain yourself while you're going along. Writing it, maybe we'll do it that way. I don't know. We'll see how it goes. We might have to change the strategy here. We might have to do it in parallel so we go through more problems. But I don't know. We'll see how it works. Okay. So we're going to meet then in room 223 on Wednesday.
This Wednesday?
This Wednesday. That's the other. Well, we have this recorded, so all the stuff we do on the document camera would be recorded. But I could delete that if you all don't want that for public release. So don't worry about that. We can fix that problem. But it is going to be something you're going to be up in front of your peers doing this, right? It's important to put some pressure on you because something isn't working. We've got to get it fixed. Okay, and I think a little bit of peer pressure is going to help with that, in moderation. So, yes, sir.
That one had a couple energy problems on it, right?
Yeah, I don't remember specifically. Here it is. So, pick up a copy of the test.
Is this the 1 through 4 or the 1 through 5 that we
This
took
is-
the common exam?
This is the 1 through 4. Now I fixed the instructions, so the instructions are not confusing like they were when I did it. So I fixed the instructions, so that shouldn't be it. Shouldn't be an impediment anyway. But, okay. Now there are the multiple choice questions on here, and I do want, when we're doing it here in class, I mean, when you're taking it on the test, you get 1, 2, 3, 4, 5, and you put it down. I don't want any explanation. I don't want to give partial credit for multiple choice, right? So when we're doing it in class, though, you should be prepared to explain why it's not 1, it's not 2, maybe it's 3, but okay, 4 looks best, and give some reason. Okay, so we can get some discussion going about these. So when you redo it, go ahead and write down some notes about why you've chosen that when you're doing it for this exercise. Not on a test, but for the purposes of this exercise. Okay? Any questions about that?
Do we still have the normal homework due Friday?
More to come. Mr. Disharoon.
Do you have the solutions?
They're in your email box.
I don't know. I either deleted them or I didn't see it. So do you have another one you can send?
If you'll send me an email to remind me to do it, please. Okay. So you should find it in your email box, or if somebody reminds me to resend it, it will be in your email box. My suggestion is you try to do it cold, and then you start recognizing that's I don't know how to do that one. I better, and then you either look it up on the book. Maybe that's good because you have to do some work. That's a little bit more effort, so maybe you learn more. Or you study the solution and you try to figure out, and be picky with yourself. When you go to grade it, be picky. Now, really, demand from yourself that you have explanation for every step written down on the page. Okay, and it's right. But be picky with yourself. If there's a difference with the solution, it may be an important difference. It might not be an important difference. You have to figure that out. Is this an important difference or not? Okay, so please pick up. There's more. Please pick up on your way out. For Friday, we're going to do the same thing with the last test that I'm about to hand out. Same again for the test on chapters 1 through 5. The one I'm about to hand out. I'm not passing out a solution yet, because I want you to, on this one, I want you to struggle a little bit more, figure out, without having the aid of a solution to go by. And then we will grade it in class together on Friday. You'll be grading it yourself on Friday. We're going to do the same again, but in that case, you'll be grading it in class, judging it yourself. How did I do on this problem and the next problem and the next problem? You'll see Mr. Tremblay is going to be doing number 3, and you're going to say, oh, yeah, he's, no, not, you know, you get it. You judge yourself, and we'll be grading it. I'll be commenting. Okay? So we'll be doing grading in class on Friday. Yes, ma'am?
So what are we doing Monday?
Monday we'll be going back to Chapter 7, Homework 3. So the homework that would be due on Wednesday, I'm shifting to Monday. I'm inserting 2 classes, which are just review. Forces, work energy theorem, Newton's equations, you know, equation of motion, right? I mean, it's strictly review. Mostly chapters 4 and 5 is what's going to be on these, but there is going to be stuff that keeps cropping up from, you know, chapter 3, formal definition of impedance, you know, definition of kinetic energy, dot products, cross products, they're all in there. Derivatives, I mean, everything is in these tests. So expressions of all of that in pretty much in the context of chapter 4 and 5. So now I might not be done. We're going to see. I mean, I'm really, I you know how much I guard jealously our time in class, right? I don't like giving it up, and here I am giving up 2 periods because I just don't like where you are. Which means something's got to give later, which is probably chapter 10, special relativity. See, I'm going to have to evaluate here. Obviously, we can't do much of this because you just have a lot to learn first year. There's a lot in this course. I mean, we still got electricity and magnetism and thermodynamics. We got a lot of stuff we got to do. So this is an exceptional thing. But like I say, maybe I'm talking it up because you're new at this. You're college level stuff. You know, it's your first semester. You got a lot going on. I don't know. I guess you can judge better than I can. Maybe some feedback from you would be helpful. I'd like to hear from you about what's going on. But you know, your peers, by comparison to the other classes that I've taught at this class before, this is the worst that I've seen. And so I'm really kind of unnerved by this. You can't, you know, sometimes, and it's not, you know, the top grade was not where it should be. I mean, there's usually some people who are just almost perfect on the test. This is not happening. Right? There's, even among the best students, there's noticeable room for improvement. Okay, so everybody really could stand to improve. Okay, so I'm going to hand these back. Do you have any questions about what we're doing here?
So this Friday we're doing the chapter 25.
Doing the one I'm handing out again. Right? I think you have the copies of the test. Did everybody take a copy of the test with you? If you don't, well, I'll bring some copies to class on Wednesday and we'll hand out some more.
So this is due. Is this next Friday or is this coming?
This coming Friday.
Okay.
So Wednesday we're going to be doing chapters 1 through 4 tests. There's the test.
Okay.
Take it home with you.
Wednesday of next week.
And Friday?
Today's Wednesday.
Today is Wednesday, so.
Hey, it's Wednesday.
Yeah.
I thought you were talking about next Wednesday this whole
Yeah,
time.
we're really
Hold on. Hold on. Hold on. Friday.
So that's
Friday.
Friday and Monday.
Good grief.